The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Yes, sir. Please go ahead. Please go ahead, sir.
Should I start?
Yes, sir.
Okay. So, good afternoon. It's a pleasure to be speaking to all of you on this channel. I'm Abhiram Ranade from IIT Bombay. I will be talking about an approach to introductory programming. Let me begin with a few comments on computer programming and its relation to engineering education. It goes without saying, really, that computation is central to engineering. For example, civil engineering has a huge number of structural mechanics computations and several other kinds of computations also. Mechanical engineering, aerospace have lots of computations related to fluid flow and several other things. Electrical engineers do circuit simulations, control theory simulations, or control theory calculations. And every engineer does computation. So this really is a point which is very, very well accepted. Another important point is that many engineering students, for whatever reasons today, take up jobs in the IT sector. And finally, perhaps the point which relates most directly to education is that computer programming is a compulsory course in most engineering curricula in the country and all over the world. So it could be said that we should teach it rather well because it seems like such an important course. Now, computer programming has several rather unique features. If you look at the courses, the subjects that a student studies all the way from high school or primary school for that matter, most of the courses are about memorizing or about understanding things. Most courses do not provide the opportunity to the student to build anything. Whereas computer programs are to be built, they work, they do interesting things. And you could say that building something is the spirit of engineering. So to that extent, computer programming is very, very close to engineering. Using a computer program, you really can explore different subjects. You can write programs about mathematics, about engineering calculations, about commerce, and even art. A standard question is, what if I do this? And such questions can be answered by writing computer programs. Most children have the urge of being able to control things, primarily because all through childhood they are being told, do this, do that. This is the first. Now, this is psychologically very liberating. Because of these features, you might think that students could probably fall in love with computer programming. But do they? Well, you know the answer. Our goal is to make this happen. We would like to teach programming in a manner that students will want to write programs as a hobby. They will want to write programs for fun. Whenever a student sees a problem in real life, he or she will ask, can I write a program to understand this problem better? Programming can help you better understand different subjects. Programming can help you explore questions such as, is this the best way to build an airport, a timetable, a schedule, or a dam, anything practically. And of course, when we teach programming to students, we want them to realize that this is a deep subject. It is difficult, but it is also beautiful. How do we do all this? This is the subject of this talk. So here is my outline. I'm going to begin by discussing the prevailing approach to programming education. Then I will come back, I will step back and talk about general educational principles. Then I will spell out our approach to programming. I will give an overview. Then I will talk about making the right first impression. Okay, you will see that making the right first impression is extremely important. I mean, if you want somebody to fall in love, you have to make the right first impression. Once you have made the correct first impression, then you have to keep the excitement going. How do we do that? We have to align the instruction of computer programming to science and engineering, and that is going to form a significant part of my talk. I will also talk about how do you teach difficult concepts. And I will talk about real-life applications, which are nevertheless within the reach of beginners, and perhaps some which are slightly outside the reach of beginners. The reason for this is that we would like beginners to get to know where computer programming can be taken, what are the kinds of things that can be solved using computer programming. And so telling them that, look, this is what you can do, but if you work a little harder, this is what you can do later, is going to inspire them. This approach that we will discuss, we have had a lot of experience with, so I will talk about that. And this approach has been documented, and detailed description is given in a book that I recently published, and let me begin with that. Okay, so this is the book published by McGraw-Hill Education. It's called An Introduction to Programming through C++. It is available in bookstores. It is available online. Okay, so let me begin by discussing the prevailing approach to programming education. Perhaps the most important problem is that there is too much emphasis on syntax. Learn language X, then learn language Y. Okay. That is not programming. Programming is something, syntax is not programming. I would suggest that instead of learning several languages, students should be taught just one modern language, but they should be made to learn it well. Another big problem in programming education is that nothing really exciting happens in the first 3-4 weeks. But if you lose the first 3-4 weeks in this manner, then the students are already bored. They have decided that this is a boring course. You may think that the first 3 weeks cannot be exciting because the students need to understand things like compiling, declarations, machine models. But that is not the only way to do things, as we will see. To drive home this point, let me mention that one textbook which is used all over India to teach C++ spends the first few chapters on just printing with desired formatting. Now, this must create an impression in the minds of the students that this is a terrible subject. This is a subject just meant for doing clerical work. Another problem is that students don't see any relation between programming and other subjects they study, or even with their day-to-day life, which is absurd because computer programming relates to everything like no other subject does, and that relationship must be brought up. That's what will make the subject relevant and interesting. Again, the reason for this is often given as that there isn't enough time to do all this. So clearly, better time management and planning are needed. Let me talk about some educational principles. Let's start about motivations. What are the possible motivations for learning that a student might have? Here is one. I cannot get a degree unless I learn this. My teacher tells me that I should learn this because I will need it later or it will be useful later. A third motivation is that I like this and I see that it is useful. Okay. I don't care about whether I'm going to get a degree. I'm seeing that this is something interesting. I'm seeing that it is useful. My teacher doesn't have to, I don't have to trust my teacher. My teacher has already persuaded me. Clearly, this third motivation is really the important kind of motivation. The others are like dragging the student. If the student is persuaded and the motivation of the student is the third motivation, then the student is going to drag the teacher. The student is going to say, tell me, teach me more. Here is a quote that I like in this context. This is by Antoine de Saint-Exupéry. He says, if you want to build a ship, don't drum up people together to collect wood, and don't assign them tasks and work, but rather teach them to long for the endless immensity of the sea. Okay, you show them what great things they will do, make them dream, and then they will do whatever you want them to. They will study whatever they want to do. That is how we should plan the teaching of anything, including computer programming. Let me talk about how learning is assimilated. Here is a very basic fact. Nobody learns in isolation. There is always something that you already know, especially when you come to college. And if you learn something new, the new knowledge will have to sit in your mind next to the old knowledge. It cannot conflict with the old knowledge. It must be assimilated with the prior knowledge. It must be reconciled with the prior knowledge. Now, reconciliation, interestingly enough, can improve the quality of both kinds of knowledge. It can improve, it can help you understand what you knew better already, but more importantly, whatever you are learning now, you will understand better if you see that it is somehow similar to what you already knew. Okay, you see how it is related to what you already knew. So perhaps some of the questions that you had earlier might get answered with the new knowledge that you are getting. Perhaps there are some similarities. So some strategies that for learning that worked earlier will work now. So by drawing on prior knowledge, we can speed up learning. We can make it less boring. Well, what kinds of prior knowledge do our students have? When a student comes to engineering, there is a lot of mathematics that he or she has learned. Arithmetic, algebra, geometry, calculus, statistics, a lot of physics, mechanics, optics, circuit theory. Okay. Other subjects also, but there is also sort of general knowledge, life knowledge, if you will say. So the student knows about networks of various kinds, so relationships between different entities. So there are family trees, there are web pages, there are transportation networks. Students should get a taste of the computation in these areas. Only then they will know the power of computation. What can they do? What can a computer do? They will realize only when they see that a computer is useful in all of these areas. Here is a very important fact that is sometimes ignored. Any subject consists of some principles, or what you might call the essence of the subject, and then there are details. The details are important, but the details are huge in number. And so there is a danger that the details will crowd out the principles, and the principles or the essence will get lost as you are discussing all the details. So the details must be taught, but they must not overwhelm the principles or the essence. So this raises the question, what is the essence of computer programming? As we describe the syntax, as we tell students where to place the semicolons and the braces, we don't want them to get lost in just that. What is it that we are really teaching them? That essence we have to keep sight of, we have to be able to articulate very properly, and we have to keep that essence as the focus of our lectures all the time. Let me now say something about how learning actually happens in the classroom. Well, some points about it. Here is a famous quote to Confucius, who says that I hear and I forget, I see and I remember, I do and I understand. So clearly, doing is more important. Seeing is important, but hearing, just hearing is not enough. So pictures are important. Animations or moving pictures are even more so. It is even more interesting if the student herself builds the animations. So there is doing as well as visualization. Dry theory can be boring and unappealing. It comes alive when you use it and you experience it. And that's when it really sinks into your mind. Okay, so based on all these ideas, let me sort of spell out our main theses, which are going to drive our approach. In my opinion, the essence of programming is to understand the pattern of the computation and express it using the appropriate language construct. So computations have patterns, languages are capable of expressing patterns, so there is a form versus content tension over here. You have to choose the appropriate form for the appropriate content. So you have to understand the content, you have to understand what form it has, and you have to express it properly. Only then can you have said to have written a program. Language learning is relatively easy if there is the opportunity to use what is learned in a realistic setting. Language learning is boring and even difficult or stressful if the only goal is to memorize and there is no opportunity for use. So we should use programming examples from math and science and even fun and art to have synergy with the prior knowledge that the student has and also the career goals of our students. In the era of cell phones, graphical input and output are very important if the students are to take us seriously. Graphics is important also for science and math visualization. Finally, learning to reason about and talk about programs, formally and informally, is important. Programming is a difficult subject in the sense of, it's a deceptively difficult subject, I should say. People can think that they can quickly write programs, but getting the program to be correct, making sure that it always works, is not an easy task. So there's a lot of reasoning involved. As professionals, that reasoning has to be documented. One programmer has to be able to describe the logic to another programmer, or even to lay people. So that vocabulary also must be developed. The concepts, the ideas of program organization, our students must be able to express. So how do we implement this approach? Well, first, our language learning is driven by applications. Typically, this is how we do things. Consider some problem X. X cannot be solved using what you know so far. So we will learn a language construct. For every language construct, it could be loops, functions, arrays, object-oriented programming features. We discuss many detailed, realistic applications. We just don't say that this statement means this. We give many applications in which that statement is useful, or in fact, it is invaluable. Okay? We discuss how to reason about each language constructs. So how do you reason about a loop? How do you prove to yourself, perhaps only informally, that the loop that you have written is correct, is going to work correctly? So we discuss things like loop invariants. In our approach, we take programming applications from many areas: math, engineering, art, logistics, games, fun. You'll see that pretty soon. Then we have a teaching tool. It is called Simple CPP, Simple C++. It contains a library which supports something called turtle graphics, which I'll tell you in a minute about. And it also supports two-dimensional coordinate-based graphics, simple graphics, okay? Simple two-dimensional graphics. It provides for graphical input, and it provides for elementary animation. You will see how to do this in a second. It is very easy to use. You might even think that it is just an alternative to the IOStream library, okay, for the purpose of graphics, rather than just character input-output. And I believe that this library is appropriate for the era of touchscreens and cell phones. Students have phones and they are already using touch on their screens and doing interesting things, and then just asking them to do character-based programs, character-based input and output. I mean, it's a throwback to some primitive era. The graphics library is useful for illustrating recursion, classes, basic constructs, and of course having fun. And finally, our teaching tool Simple CPP implements, so to say, a new statement. Okay, a statement which is not really present in C++. Okay, and this is the so-called repeat statement. This statement will serve like training wheels, and it can be taken out later on. But it's just a very simple statement, and it really helps speed up things and get students to do interesting things from the very beginning. Okay, so our approach uses C++, and so I guess I should make some comment about why C++. So programming could be learned in one of several languages. I guess the main point that I want to make is that you should pick some modern language. It doesn't really have to be only C++. It could be Java, for example. But certainly, it should be a modern language. So it should be C++ rather than C. It would, I think, today, you are torturing your students if you teach them C. Some of the reasons for this are as follows. If you are doing string processing, C++ string class is much safer than the null-terminated char arrays of C. The string processing in C++, the string class, eliminates many bugs. So your students will just have a much more pleasant, a much more enjoyable experience as programmers, as learners. There is no need to really fall into every pit, every trap that is created by null-terminated arrays. By using constructors, proper initialization can be forced in C++, so there is less danger of forgetting. The standard library provides many features that you want. For example, lists, priority queues, algorithms like sorting, and these algorithms are customizable. Doing things like this is horrible. It's horribly difficult in C. So you should be kind to your students and teach them C++ and not C. The dynamic memory management in C++ is likely to reduce bugs, but if you use the standard library, you may not even need dynamic memory management. It will happen behind the screens for you. And of course, the object-oriented features are there. Encapsulation, inheritance, polymorphism. They indeed make it easier and safer to write and extend programs. But even without object orientation, you should teach C++ rather than C. Now, I said earlier that Java is also fine, but remember that C++ is much, much faster than Java. A recent study of the ACM ICPC programming contests, shows that even when given the freedom to program in Java, people prefer to program in C++ because it is much faster. And professional programs, really high quality programs where speed is important, are definitely written in C++. All right, so let us now talk about how we go about teaching, and let us begin from the day one. The important point for day one is to get to the essence. If you want to make a good impression, you have to talk about the subject. You have to get to the key parts. If you don't do that on day one, students are going to say, oh, this is a boring course, or this is an easy course, an easier course than it really is. This is a time pass course. So students will have all the rich vocabulary to describe things that they don't find serious. So they will start using all those adjectives for programming, which we don't want. So what we do is we introduce the course or introduce programming using turtle geometry. Turtle geometry was invented in the 1960s by Seymour Papert as a part of the Logo programming language for teaching programming to children. I find that the ideas are quite useful for teaching programming to adults as well, and you will see that in a minute. The turtle in this is a symbolic animal that lives on the screen. It can be made to move as per the commands that your program issues. It has a pen which draws on the screen as the turtle moves. So, as you might guess, the goal of turtle graphics is to draw interesting pictures on the screen by driving the turtle around on the screen. Here is a very simple program fragment. The first statement, start turtle graphics. Turtle sim starts off turtle graphics. So this will create a window on the screen, and the turtle will be present at its center. Typically, the turtle is shown as a small red triangle, but sometimes you may also see a picture of a turtle. But in our C++ package, simple CPP, the turtle indeed appears as a small triangle. We'll see this in a minute, but I just want to explain this program first. Forward 100 is a command to the turtle to move forward by 100 pixels. So if the turtle is, say, present somewhere over here, and when it comes up, it is pointing to the right, forward 100 will cause it to move forward by 100 pixels. So if it is here, then it will move to this point. And its pen is down, so that means it will draw a line. Then the next command says right 90. So it is facing right, but it is asked to turn right by 90 degrees. So if it is facing right, and if it turns right by 90 degrees, then it will now start pointing in the downward direction. The next command makes it go forward again. So if it was over here, then it goes down now. Again, it turns right by 90 degrees, but now it will start pointing to the left, in fact. So right 90 says you are facing in a certain direction in which you are moving, and with respect to that, turn that many degrees to the right. Okay? So it moves forward again, and then again turns right, and then again goes forward. Again, it goes forward 100 pixels. So what do you think that this did? Anybody will say that this draws a square, and indeed it does. Okay. This can be the first program that you introduce the course with. Well, actually, the first program is slightly different. Okay. So here it is. Here it is in full. So the very first statement is hash include simple CPP. Okay. So simple CPP says that I want graphics functionality. I want the graphics functionality included. Okay. Now, those of you who know C++ know that we also need to include other things such as IO stream, and we have to say that we are using the namespace std. Okay, so this gets included by simple CPP. So these details, IO stream and namespace, are being hidden right now. Okay. The next statement, okay, well, so it's not that namespaces and IO stream are unimportant, but they are not important on day one. They are details. Remember, we want to get to the interesting stuff on day one. We want to give the taste of what programming really is to the student. And in that sense, the namespaces are not important. The next statement, main program, just says that what follows is a main program. Now, those of you who know C++, and I assume that means almost everyone, knows that there is no such keyword in C++. Well, this is a C++ macro, which is a part of simple CPP, and it automatically expands to int main. Why are we using this? Well, look at int main. What is int? You don't want to explain that to the student on the first day. What are those parentheses doing after main? Why are there those parentheses? We don't want to explain that either. Okay, so the rest of it is the program that you already saw, okay, except for this wait. Wait is there just so that the turtle stops and actually waits. Because if you didn't put that wait, then the whole thing would happen so fast that you would not even see it. Okay, so let's now do a demonstration. Okay, so here I have the program already there, and I'm just going to execute it for you. So /square. Okay, so square is the name of the program that I showed you, and let's see what happens. So as you can see, the turtle did exactly what we thought it was going to do. Okay. All right. So let's go back. Okay, so let's come to the second program for the first day. Now this program has forward 100 and right 90, but it is put inside this repeat. Now having seen the first program, okay, you probably know what this means or what is the intention behind this. And indeed, this program is introducing this so-called new statement called repeat. What does the statement in general look like? Well, the repeat is followed by a count, okay, and then in parentheses, and then in braces, the statements to be repeated are put. Now, why are we using this? Well, first of all, the motivation for repeat is very clear. Instead of writing 100 forward 100, right 90 4 times, we can just write it once. Okay. So it saves typing. But more interestingly, so it is sort of acknowledging that there is some symmetry in whatever it is that we want to do. And so the symmetry is being represented. And of course, this can come later. As you know, there are loops in C++ which will allow you to do all these things. But the for loop of C++ is a very complicated object. It cannot be taught to students in the first day. By teaching this repeat, the students can understand it very quickly. It's absolutely painless. And once they have the repeat, they can really write interesting programs from the very first day, as you will see in a minute. Okay, the repeat is implemented using C++ macros, which get loaded when you include simple CPP. Of course, you don't have to tell how the repeat is implemented. That can come later when we talk about C++ macros later on in the course. Right now, you can just tell them that, look, there is this statement called repeat, and it just repeats whatever is inside. And students have no difficulty understanding this. Here is another program for D1. So it starts off with turtle sim, opening the turtle simulator. Then it repeats 10 times. Okay, so what is it going to do 10 times? Well, inside the repeat 10, there is a repeat 4, forward 100, right 90. Okay, so this clearly is drawing a square. After that, it is turning right by 90, by 10 degrees. So what do you think this draws? I ask this question to my students, and they puzzle over it, and they give me the right answer. Most of them give you the right answer. Why is it? Well, it's an interesting challenge. And in fact, this is an interesting program. So let's see it also. So this program I have also compiled, and it is called another day one program. And let's see what it does. So it draws a square, another square, another square. And it stops. So it fans out the squares in this manner. So you can see that already we are drawing interesting pictures. It is already looking like fun, but it is not. It is not trivial either. There is some method to this madness. Okay, so let's take stock of what has happened on day one. What have the students learned? Students have learned control flow. They know now that statements are executed from top to bottom, left to right if you will, and left to right if you will. They have learned elementary iteration, including nested iteration. By the way, so this program has a repeat nested inside another repeat. So I will explain, when I teach this, I will explain what this does in a little bit more detail. But the beauty of it is that the students intuitively know what this will have to mean. And then they execute it, and then they see that their conjecture is correct. And so this goes by with very little explanation, or if the students are excited, which they should be, with almost no explanation. So they have learned iteration, and they have also learned nested iteration. Now, nested iteration is not an easy concept, but we have got to it on the first day. They have understood the basic idea of syntax, spaces, indentation. Okay, all that you don't really have to dwell on. You can say, maybe you can make a remark or two. But the point is that the students are now excited about doing things. So all these things will fall in place without you having to drill them, because they will want to do it. They will want to learn it. They will take a program which is already there. They will copy it. They will modify it, and since the whole thing makes sense, they will not be worried or they will not be bothered about all of this. here is another really important lesson. The students have learned the importance of observing patterns in what is to be accomplished and expressing those patterns using repeat. For drawing that fanned set of squares, this was important. Otherwise, it would have been a really painful program to write. For another, if you want to draw a 100-sided polygon, do not write 100 statements or whatever, 200 statements. Just put them inside a repeat. This, in fact, is an extremely important activity while designing programs. Isn't this the essence of programming? Matching the pattern of the computation to the constructs in the language. So one kind of pattern you have shown to the students on the first day, and you have also shown them how that is to be expressed in the language. On day one, you can give some interesting homeworks. So you can say, draw a chessboard or draw a circle. Well, what is a circle after all? It's a circle. A circle is a limit as n tends to infinity of an n-sided polygon. In practice, n doesn't have to become infinity. In practice, even n equal to 100 or so will look like pretty much like a circle. Now, what I have shown will need some high school geometry. However, if you take any application of programming, you will need some domain knowledge. So, relating domain knowledge to programming is absolutely important, and we are doing that. Moreover, you will see that students actually love to use what they already know. Because all the geometry that they have learned is sitting in their heads and doing nothing. And now it suddenly is going to come out. It's going to find an outlet. Students are happy to do all this because they can see interesting things happening and they can feel the power. Okay, so you began with a bang. What do you do next? Now, the topics for day 2 or week 2 are like, how does a computer work? Okay, you have to talk about data types, you have to talk about variables, assignment statements. So clearly, there is some information that has to be given. In the standard teaching style, okay, this information sort of causes an overload. So there is an overload about number representations, statements. Okay, what happens if you assign a floating point number into an integer? Okay, all of that. Okay, so all of that needs to be done. The question is, can we make it interesting? And can we put active learning into it? Rather than just memorizing it, can we do things with it? Can we do interesting things as we learn that material? So remember that you have already taught your students the repeat. Now, repeat can make for interesting programs. For example, here is another picture that you might want to draw. So this is going to repeat 10 times, forward I and right 90. So it's beginning to look like a square. However, after each step, I is changing. Remember, we have already learned, we are just about doing this when we are looking at the assignment statement. And we are doing self-assignment, okay, reassignment. So the value of I is changing. So what does this draw? Well, if you do it, you will see that it draws a spiral. So self-assignment or reassignment is an interesting is a slightly difficult concept because this statement doesn't make sense in mathematics, whereas it is important in programming. Okay. But if you put it inside a code which draws a picture, then students will understand it right away, and indeed they do. If you have the repeat, then you don't need a loop to be able to do sums of series and things like that. Remember, students already know the series for, say, calculating E, and so they can write this code. So this is what they can do on day 2. Okay? So the key point is that rather than bore them, you get them to do things which they find interesting. Then they will then they will come along with you. Otherwise, they will drag you, they will hold you back. And of course, you will complain that, look, there is too much syllabus and I can't finish the whole thing very quickly. Okay, I don't have time to do interesting things. In the third week, or second week, whatever, okay, we do introduce coordinate-based graphics. So creation of graphical objects, manipulation, and also graphical input. So here is a quick summary. So this statement, circle C1, 200, 225, 25, is just going to declare C1 to be a circle, which is centered at these first two numbers, the coordinates given by the first two numbers, so at the point 200, 225 on your screen, and its radius is going to be 25. So that is what this statement does. So if you want a circle, you should write a statement like this, and you can give it whatever name. This is a statement for creating a rectangle. So these are the center coordinates, and this is the width, and this is the height. Now, r1.right, again, you give the angle in degrees over here, will cause the circle to rotate right by 45 degrees. C1.move, sorry, the rectangle to move, rotate by 45 degrees. C1.move will cause the circle to move by 10, 20 degrees, by 10 pixels and 20 pixels respectively in the x and y directions. Here is the statement which allows you to do graphical input. You can write z equals get click, and this get click will cause the program to wait until the user clicks on the screen. After that, z will be assigned the value, which is 6556 times the x coordinate of the cursor at the point of clicking plus the y coordinate of the cursor at the point of clicking. In other words, the most significant 16 bits will be the x coordinate, and the least significant 16 bits will be the y coordinate, if z is a 32-bit number, as it is here. Now, this has a lot of excitement value. As you can see, you can create objects on the screen, and then you can move them around, so you can do animations. But there are many educational goals also achieved. So implicitly, we have introduced to constructor and member access syntax. Of course, we are not going to tell them that this is a constructor for C1. We are just going to say that, look, this creates a circle. So this technical notion doesn't have to come now. It can come later when you talk about structures or classes or whatever it is. But they are becoming familiar with this kind of syntax. r1.write 45 is the dot notation, which is also important in C++, and they are beginning to become familiar with it. So now, if you use this and if you practice it, if you include this with repetition, then you can do very interesting animations. So, in fact, once you have this graphics, you will have a huge field or a huge supermarket from which you can get interesting problems and excitements for weeks to come. So, for example, here are the assignments that could be given in third week, or you could discuss in class. In fact, they are discussed in the book. So I have a ball which I want to toss in the air, and then I'm tossing it in a certain direction, so it goes up and comes down according to gravity. So I want to show that on my screen. I can do this, and I can do it in 10 lines of code, and I'll show it to you in a minute. Similarly, I click points on the screen, and I want the line to be fitted. This can be done in 20 lines of code. Again, I'll show you the code. Okay. So I'll do the demo, but let me just point out one thing to you. So the mechanics involved in the projectile motion are already known to the student. Similarly, how to fit a least squares line to a set of points, okay, is already known. They have learned it in standard 12th. Okay. In any case, the book does describe it also. So the book is reasonably self-contained. Okay. All right. So the important point is that mechanics, math, and programming are beginning to mix as they should. Okay. There shouldn't be compartments. Okay. So these subjects are merging, and students will ask questions based on one subject about another subject. And that is where interesting thinking will start happening. Okay, so let me show you the projectile motion code. Okay, so here it is. So get click. So we will click, and that will be the starting position. Then our projectile will be a circle. It will have its pen down so that we can see how it moves. These will be the initial velocities, and then we'll just keep on moving the projectiles. So we'll change the vertical velocity, and then we'll keep on moving it. So that's it. Okay. So let's run this. Okay, so I have to first click. So for example, I click over here. So that circle is going to go up. It has a horizontal velocity, so it will keep moving with the horizontal velocity, but it will have gravity acting on it. Okay, so let me take the other one. So in this, I have to plot some points on the screen. So the line which has the best least square fit with these points is drawn. So this code is also a fairly simple code. So let me show that to you. Okay. So this is the code. So I'm plotting 6 points, and I'm going to create circles wherever the user clicks. Okay, so there is a get click, and then this is just the implementation of the formula needed. So the formula is going to update certain values, and then that line is going to be plotted. That's it. So the student already knows this, and what we are doing is helping him or her use it. And that use is always very, very exciting. Okay, what do you do next? Well, there are the standard statements like if and select to be executed, to be understood. So we introduce them, say, by doing tax calculation. Oh, there is an interesting thing that you can do once you know the if statement. You can implement buttons. So students are used to seeing buttons on their screen on which you can click. Well, what is all that anyway? So you need to draw a rectangle on your screen, and then you have to check whether the click that you just made, its coordinates lie inside a rectangle. So this is also a simple thing, a simple exercise that we do. You can check whether a number is prime already, and you can do another nice mechanics related problem, which is a ball bouncing in a box, and I'll show you that in a little bit. Okay, so you have loops, while, do, and then there are the break statements, and then there are there is the for loop. So we take a lot of examples for this. We do a very different ways of mark averaging. Okay. So not just one version, but different things. And so we discussed many codes using these loops, how to compute digits in a number, deciding whether a number is prime, greatest common divisor, Euclid's algorithm for it. We spend a fair amount of time arguing that it is correct. So as I said, students need to know how to argue correctness and persuade themselves as well as persuade their friends. Numerical computations of sine, log, etc. are definitely within the reach. Newton-Raphson method has already been learned by the students in 12th standard. Functions have to be taught, so recursive and non-recursive versions of Euclid's algorithm are considered. Functions to draw polygons or drawing text are written. And an interesting example of functions is a function for drawing trees, which you might think of as visible recursion. Okay. So this is actually an interesting topic because it shows off how graphics is very useful. Recursion is considered a difficult topic. People have difficulty understanding how recursion works. With graphics, recursion becomes pictorial and therefore easier to understand, in my opinion. For example, I can think of a tree as being a trunk plus two small trees on top. And this observation about the structure of the picture can be expressed in the structure of your program. So here is a function which draws a tree. Okay, so it draws some tree with so many levels. So levels are how many times the tree will branch above. So never mind this statement. This statement has been put just so that we will see what goes on. But this is really the important part of the code. So this statement is going to draw the trunk. Okay? And then here is the small tree, and here is the second large tree again with levels minus 1. So whatever levels was, we are going to call it with levels minus 1. And this is going to be aligned at 45, an angle of 45 degrees to the left, 15 degrees to the left. Okay, and this is going to be aligned at an angle 30 degrees to the right. So again, 15 degrees to the original angle. So let's see this in action. So the program is okay, so the trunk has already been drawn, and then at that point the turtle has waited just so that the recursion becomes easier for us to understand. So if I now click, it will draw one of the two small trees. Okay, so see this, the big tree is made up of one small tree, and I click again and it will draw the second small tree. So the details of this are not important to understand. You will need to stare at the code a little bit to figure out what exactly each statement is doing. But the high-level point should be obvious, that a tree can indeed be thought of as two small trees on top of a trunk. And in fact, our code reflects exactly that pattern, and recursion is exactly the pattern to express this. Okay, now inheritance is another difficult topic. So this also can be expressed explained quite nicely using graphics. The big problem one of the major problems with inheritance is that examples are not very easy to come by. There are examples, of course, and there are standard examples, and those standard examples are indeed done in the book, discussed in the book, and I do discuss it when I teach. But how do you make students use inheritance? How do you construct a good motivating example and an example which forces students to use inheritance? Okay, so simple CPP provides a composite class, which is actually an abstract class for creating composite objects. So for example, this is how it works. So I want to create a wheel. A wheel is made up of a rim and spokes. So I can create a wheel class by inheriting from the composite class. Okay, so the composite class is sort of like a container class, which allows me to put together individual graphics objects and then make a bigger graphics object out of it. So this is what is going to happen over here. So in the constructor, I'm going to construct the rim, so I'll have a new circle constructed. Okay, and then I will construct the spokes. That's it. So once I do this, I have a wheel class, and I can create instances of it. I can move those instances, rotate them, all such things. And you will see an example of this fairly soon. Now, in the book and in your course as well, I expect that there will be some advanced applications that you will do. Okay, so some applications of programming. So for example, the book discusses in quite detail an application for graphs. Graphs are used in circuit theory, finite element computations, and so on, and so they are important for students to understand. But you can teach that. The point is that you can teach these things even in the elementary programming course, and students will understand them and will appreciate them because they can now see the power. So the book has substantial discussion on how to represent circuits, how to calculate their values, how to solve the circuits. Okay? And the page rank algorithm is also being discussed. Another important application that we do is gravitational simulation. The idea of this, the science of this is known to the students. So they have to put together those ideas. Well, those ideas and a little bit more. So what is the input? The input is the current position, velocities, and masses of stars. And as output, you have to show how they move over time. Now, the students learn this in physics, so you could see it for yourself. Historically, this gravitational simulation is very important. It was perhaps the problem which led to development, which was instrumental in developing a lot of science, all the way, not just all the way from Newton. Now, the marching over time method can be used, okay, but it turns out that there is a slight modification needed for it, which is discussed in great detail in the book and which the students can understand. And then the program is given. The program is fairly straightforward. One interesting thing that this application does is it develops a class for representing three-dimensional vectors. Okay. So now, if you have such a class, and if you overload operators, which is something that C++ gives you, then you can write vector assignments like S is equal to UT plus half AT squared. So this turns out to be a good example of overloading operators as well. Another exciting application that has been described is the layout of math expression. So for example, you have this mathematical expression. You want it drawn in this manner. How do you do it? Where do you position the horizontal bars? Where do you position, how large are the bars? Where do you position the characters? So this turns out to be an example of recursion, including parsing that expression. And it's a good example of a tree-based representation of mathematical expressions. Once you have this basic, you can do symbolic computation, and you can also do things like, if I have a function of x, how do I differentiate and integrate it? Don't get too worried by these topics which seem difficult. First of all, they are explained in great detail in the book. But more important, you may not teach them in the example. However, you should give to your students some material, at least so that the better students, the more ambitious students, can read it up. And this also turns out to be a good example of inheriting with and without inheritance. So you can show the power of inheritance. Discrete event simulation is also another application which has been discussed. Simple idea is, suppose you have some system, and how does it behave under random stimuli? So for example, it could be a toll plaza, airport, and is there congestion in that? So for example, for aircraft, you have to make sure that they don't go too close on runways or taxiways. At any time, there must be at most one aircraft at gate. So such considerations you have to model. Again, this may not be something that you may do at great detail in your very first course, but this is an important application of programming, and ambitious students can certainly do this by themselves after the first course, and probably in the second course, other students can be made to do it. So there are some interesting language extensions that C++ has called lambda expressions, and those can be very, very nicely used in this application. And of course, it requires you to understand resource management. So for example, if you have an aircraft landing, then you have to allocate a gate for it, and that gate should not be given to another aircraft at the same time. So keeping track of these things are important. This discrete event simulation also simulates a system of cyclists, which effectively finds the shortest path in a graph, actually a shortest path in a map, and it uses Dijkstra's shortest path algorithm. So the chapter actually ends up giving a vivid example, a vivid explanation of Dijkstra's shortest path algorithm. Again, This is definitely within the reach of at least the bright students. Okay, so now I'm going to show a longish demo which shows some of the things that I have already talked about. Okay, so here is the turtle drawing an interesting pattern. The question about this is how much should the turtle move, rotate, how much should it move forward so that the pattern closes back on itself. So this is an interesting exercise. Here is the turtle drawing something called the Hilbert space filling curve, named after the famous German mathematician. As you can see, it has a recursive structure and it can be made to fill as large a region of space of the plane as you want it, So again, it's a rather nice, interesting example of recursion. All this is done in simple CPP. So here is a tree being drawn. It is really similar to the tree that you saw earlier, except now the branches are being made of unequal length. And as you can see, the turtle is making copies of itself at different points so that they look like leaves. Okay? But it really is a very, very simple, very short program. So that is the beauty of recursion, and that is the power of computers. That very tiny things, very small things can do something rather remarkable. Here is a more conventional tree that is being drawn, and you can see that you can have numbers also placed at different points. And here also you can see that the left tree is drawn first and then the right tree. So this is built using that composite class. So first of all, the wheel is whatever I showed you, but the car class contains two wheels as well as that polygonal body. And the car movement, you can make the car move just by showing move and rotate, just as if it's like a rectangle. But the interesting thing is that when the car moves, you can arrange for the wheels to turn. That is again the power of recursion and inheritance. This is the bouncing ball example that I talked about. So it is interesting to draw, and you will see now that there is something more interesting that happens. So after a while, the ball is going to get into a pattern. It's going to move over the same tracks. So this might come as a surprise to many students. And this is the aircraft simulation that I was talking about. Okay, here, the aircraft are drawn a little bit bigger than their actual size might be, just so that you can see them. And that's only so that otherwise it's hard to see. But they are really being kept apart. And as you can see, when there aren't two aircraft on the takeoff runway at the same time. The previous aircraft actually waits there until the previous aircraft has moved out. So that is in fact what aircraft are supposed to do on runways. Finally, the gravitational simulation. So this is done using the method, not the very simplest possible method you might think of, but just a small refinement which has been described at great length in the book. Okay, so we are more or less done. Let me just make basically some more concluding remarks. Okay, so several other algorithms are also discussed in the book: merge sort, backtrack search, game tree search, advanced features of C++ like reference counting. Okay. I already said that circuit solving and page rank. Okay, Newton's Raphson algorithm for multiple dimension is discussed with great amount of explanation. So I think at least the bright student should be able to follow them. The book has been used in the Introductory Programming course at IIT Bombay during the development and after publication. It has been used in an IIT Bombay edX massively open online course which has been taught several times now by Professor Phatak, D.B. Phatak, and Professor Supratik Chakravarti of IIT Bombay. It is currently being used in the Introductory Programming course for all branches of engineering at the Vishwakarma Institute of Technology, Pune. Students have used simple CPP graphics to do many exciting projects, games, puzzles, graphical editors. One student did a circuit editor, so you could drop resistors and capacitors, and then his program would actually solve the circuit. Simple CPP is available as a library for Unix and embedded in an IDE for Windows and Unix. Just do a Google search for Simple CPP, and you will get to my page from which you can download Simple CPP. Chapter-wise slides are also available to instructors. Again, you can get to them. You can just search for that and you can get to them, or you just contact McGraw-Hill representatives. To conclude, I just want to point out that pictorially observing the effects of iteration, recursion drives home the concepts very effortlessly. Students reported that after programming math problems, their understanding of math and programming both improved. There is substantial discussion of style, different ways of writing the same logic, and readability in the program, in the book. To become a good programmer, you must write many, many programs. Many interesting exercises are given after each chapter for you to practice. And the book contains a lot of applications which will help students who are doing projects and stimulate their imagination in general. To conclude, let me read out a quotation from Charles Anthony Richard Hoare, an eminent computer scientist. He says, or he asks, what is the central core of the subject computer science? What is it that distinguishes it from the separate subjects with which it is related? What is the linking thread which gathers these disparate branches into a single discipline? My answer to these questions is simple. It is the art of programming a computer. It is the art of designing efficient and elegant methods of getting the computer to solve problems, theoretical or practical, large or small, simple or complex. It is the art of translating this design into an effective and accurate computer program. Thank you. And now I can take questions. Mr. Noori?
Yes, sir.
Yeah. Can I take questions, if any?
Sure, sir. Yes. We are waiting for any questions.
Okay. So did this go okay? I mean, there was no problem, right?
No problems.
Okay. I assume you would have told me if there was.
Yes, sir. Yes.
And I probably haven't. Could you perhaps tell me what it is about? And then if I can say if it is related or I can make a comment.
Basically, an instant feedback as soon as you program.